Hi and welcome. This is Bits of Deep Learning and I'm Andrea. In this video I'll break down the paper Shortcut Learning in Deep Neural Networks by Robert Gayros and others. In the last years, performance of machine learning algorithms increased dramatically and in many cases exceed that of humans. From natural language processing tasks like the squad question answering dataset to image recognition on the ImageNet dataset. But are these algorithms really better than humans in answering questions and recognizing objects? Well, maybe not. Looking at some results obtained by different models, sometimes we can encounter very strange results. For example, these images recognize sheep, teapot, a pneumonia on the shoulder, and predict an answer from an irrelevant text. So why are these models predicting such wrong results when they should be better than humans? It would be very helpful to understand if these cases come from an independent phenomena or if they are following a common unintended strategy. Shortcut Learning in Deep Neural Networks, the paper by Robert Gayros that we are about to discuss in this video, address the issue of shortcut learning. And in the paper, they show that shortcut learning is the problem behind the unusual result that we have just seen. So exactly what is shortcut? As stated in the paper, quote, shortcuts are decision rules that perform well on standard benchmark, but fail to transfer to more challenging testing conditions, such as the real-world scenarios. Just to give you a concrete example, in the previous images, the shortcuts are the use of background to recognize the primary object, features unrecognizable to human, hospital token, and blindly looking at the last sentence, ignoring the context. So, why deep learning learns such shortcuts instead of the intended features? That's because the shortcuts, as the words say, are easier to learn. That's it. It's a shortcut to the final solution. It's the principle of least effort. Think about it. If the goal is just to get the highest score in an exam, wouldn't you just find a shortcut in the final test? In this way, just with a shallow learning, you can achieve high score. Shortcuts may be based on dataset opportunities that unfortunately will induce a model to fail to generalize as intended. For instance, if in the training set the cows are always seen on the grass, then the machine learning algorithm will be prone to learn contextual biases. This means that the algorithm will fail to predict a cow if it is on the beach. Another example of dataset bias is a high-frequency pattern that are invisible to human eye. Also, the algorithm may find the shortcuts in the decision rules, as it may find it easier to discriminate objects based on the texture instead of the shape. For example, a model trained on ImageNet will predict this image as elephant instead of cat. But if the learned function is expected to be robust and general, the use only of texture to discriminate objects is very problematic. So unfortunately, shortcuts make the decision process embedded in the deep neural net highly sensible to small perturbations. And as you can see from the images, just some innocuous distribution shift like image rotation, adversarial example, or change of the texture that interact with the shortcut features can completely derail the prediction. So going back to our original question, we have seen that machines are not better than humans on general tasks like question answering or object detection, but it seems to perform better on these benchmarks thanks to these shortcuts. It's also important to note that most of the time shortcut learning goes unnoticed, as deep neural nets are very hard to explain and interpret. And when we see algorithms achieving good or superhuman performance, we are happy with it, thinking that the model actually learned the intended solution. But it's wrong. As humans, we follow the wrong assumption that at an algorithmic level, human-like performance implies human-like strategy. And citing the paper, quote, "We should never attribute to high-level abilities that which can be adequately explained by shortcut learning." What does this mean is that in absence of rigorous tests, it's more likely that the deep learning model exceeded human capabilities on a specific dataset thanks to shortcut learning, but without actually learning the underlying task. Now, before seeing how to address the shortcut learning problem, let me contextualize it better also in reference to overfitting. In the paper, three main spaces of decision rules are identified. The first is called training solutions. It includes overfitting solutions that are function learned that yield good results only on training images. The second one is called shortcut solution. These solutions score high on standard benchmarks leaderboards, but include the shortcut solution that don't generalize well on different examples, the so-called OOD or out of distribution data, but only on independent and identically distributed test data. The third one is called intended solution, and these decision rules work well not only on independent and identically distributed test data, but also on the out of distribution test where shortcut solution will fail. And whereas at the moment the majority of public benchmarks are fine with the second space of the shortcut solution, we should commit for the small red dots of intended solutions. What I mean by that is that we should revisit the usual split of training and test data. Usually, training set and test set are drawn from the same distribution, and in practice, this is done by randomizing the split between the two sets. But as we already mentioned, as long as the tests are performed only on identically and independent distribution data, it's impossible to distinguish between shortcut and intended solution. Thus, we have to assess the model on challenging test set out of the distribution with respect to the training set. And we have to employ rigorous testing to be sure that the intended solution has been learned. That's very important as we adapt and rely more on deep learning applications. We should test against deep transformational learning, not against surface learning. And as the authors point out in the paper, quote, "We must not confuse performance on a dataset with the acquisition of an underlying ability." So to build an effective test set, in the paper they propose three key pillars. One, there needs to be a clear distribution shift that may or may not be distinguishable by humans. Two, it should have a well-defined intended solution. And three, this test should be very challenging for the majority of the current models. Aside from the assessment, the neural net can be optimized directly for the intended solution. For example, with domain-specific knowledge like augmentation or adversarial example, or also with domain adaptation and generalization, where multiple distributions are observed during training, and the model is supposed to generalize to a new distribution at test time. So in conclusion, a true generalization is missing all across machine learning, but it's possible to reach it with rigorous out-of-distribution benchmarks that help to distinguish between intended and shortcut solutions. I hope you found this content helpful, and if you want more details on the topic, check out the paper linked below. I'm Andrea and I wish you a good day.